to our last session of the Parallel Symposium, Parallel Computing Symposium. So in the last few days, you have heard about how Microsoft is going to deliver solutions to help you build parallel applications. And this morning, you heard a little bit about the end game. Applications matters. So we have an application architect giving you some principles and guidelines on how to think about parallelism. And we have Jerry from Intel giving you a vision of what is in store for us for the future. So in this session, we're going to have a distinguished panel to talk about the future of parallel computing. So what is beyond what we have told you in this PDC? So you have seen this slide from David Callahan's presentation. Our goal is to take parallelism mainstream, so it is not only held in the hands of the games developers, the experts, people who have an interest in research, government work, and so on. So a term that we used inside Microsoft is how do we take it mainstream, or how do we democratize parallel computing? So today with me, we have a very distinguished panel. And first of all, we have Intel James Reinders, who will take us through the innovation that they will put in threat building block, which is a portable library aiming at improving performance for C++ applications and on multiple processors. And then we also want to talk about how do we ensure correctness. Now, a lot of the popular programming languages and programming models, they support the use of shared state. But shared state is very brittle, and it is very difficult and error-prone and so on. So how can we sidestep that? How can we just skip that totally? So we have two topics related to correctness. One is software transactional memory, and then the other is agents. So for software transactional memory, you'll hear perspectives from both Microsoft and Intel on their approaches and their implementation, research, thinking, and so on. So again, we have James Reinders from Intel and Dave Detlefs from Microsoft. James is the Chief Evangelist and Marketing Director for Intel Software Division. And Dave Detlefs is our Principal Architect in the CLR, the Common Language Runtime, and he has been a key contributor to Microsoft's transactional memory. And then Nicholas will talk to us about agents. How can we use agents to implement inter-component communication? And then finally, we cannot go to the moon or land on the moon without instrumentation. So Sean is going to talk to us a little bit about tooling. How can we bring everything together? How do we help people to design, optimize, validate, and so on? And so we are shipping some tools in Visual Studio 2010 to help you with debugging, testing, parallel code. And Sean will talk to us about what is in the future of our tooling strategy. So with that, I'm going to turn this over to James, who will start with talking to us about Intel's threat building block.
Thank you, Selena. So since I work for Intel and think a lot about hardware, I thought I'd start with some numbers. Don't know if all of you have thought of it this way, but one of the things that's rather astonishing is that if we go back 3-4 years ago, there weren't very many multi-core machines. There weren't very many parallel machines, especially in most people's hands. There maybe in servers and supercomputers, certainly, but there weren't. That's all gone now. This is some data from IDC that shows just how extreme it is. Now, some people in the industry will say, well, Intel's forcing the multi-core chips down people's throats. Gosh, I wish that were true. We build things and see what people buy. And the multi-core chips have been a big hit. In fact, I think we've been a bit surprised ourselves at just how fast, especially in all segments, even mobile, even laptops. So if you're writing a program today and it's not parallel, you're missing most of the machines being sold today, and certainly the installed base. So I like numbers. I'm an engineer, so I like numbers. So I thought I'd start off with that. But let's talk about programming. So I've been doing this parallel programming thing for a long time, and I get to visit customers, and there are two reasons people fail with parallel programs. Two big reasons. One is the program becomes non-deterministic. They can't figure out how to debug it, correct it. And then when it comes time to ship the application, of course, there's an engineer that worked on the parallel part that's pressing management and the QA team to ship it, and it kind of comes down to, do you feel lucky? And I've seen a lot of apps get parallelism added to it and then don't ship because they're too nervous. So we definitely need to do something about that, and there's a lot of tooling and so forth and techniques to steer us away from this problem. The other one's scaling. Oh gosh, how often have I heard it runs faster on 2 cores than 1 core, but for some reason it runs slower on 4 cores than it did on 1. So scaling can be a real challenge, and again, the right techniques, the right tools help with that. These two are really critical points. So I think everything we're going to discuss quickly on the panel and then get to questions, come back and try to address these two fundamental issues. Any solution to parallelism has to attack at least these two. There's a few more too. So I figured I'd start off at the tooling level since that's most important, talk down quickly. We'll get down to things, and then we'll come back to tooling at the end in much more detail. My particular group's been involved at providing tooling in high-performance computing, which is a very heavy parallelism world, for some time. But we just announced our Parallel Studio in August, which is a new project that we had embarked on a couple of years ago. It's just coming out now. And people often ask me, what's different about this? And I said, wow, that's, the technology underneath is very similar, but when you start talking about programming parallelism outside the high-performance computing space, outside the extreme scientific space, you come up with a lot more challenges. And so we've been looking very hard at what Microsoft's doing and seeing very good things and wanting to be very supportive, be a big part of being in the Visual Studio environment and helping move parallelism into a space where it also matches up with productivity. So we've, very similar to talks you heard this morning, looking at key problems of the whole life cycle, everything from debug and coding to tuning and debugging. But I want to zero in and talk about one thing in particular. So all of these tools we're doing are going to sit on top of the concurrency runtime. And I want to talk about one tool in particular, threading building blocks, and what we're doing there and what we see as some of the challenges in the future. We couldn't be happier about concurrency runtime. We've been implementing different solutions like threading building blocks in OpenMP, and over time, if every one of your solutions creates another thread pool inside your application, this is not good. Concurrency runtime solves that problem, and David Callahan was even hinting at things that will have to happen in the operating system. And give it time, and the whole stack is changing a bit. So for us as a tooling provider, having the concurrency runtime is a big step forward for us. It lets us innovate in a higher level space and count on a consistent underpinnings for us. So the threading building block project, I know some of you are familiar with this project. We've had out for a few years now. It's been very popular for us, and it tries to answer a simple question. How do you extend C++ for parallelism? Well, maybe that's a little bit bold, but there are going to be a lot of options available to C++ programmers, but we took a look and said, what are the key problems with C++? So we've worked on algorithms, concurrent data structures, a lot of things you've been hearing about. I want to talk a little bit more about how we view that. This has been ported, Windows, even Xbox 360. We've got a port for that, which was done by a gaming company in Russia that wanted to support both the PC and the Xbox 360. And this all sit on top of concurrency runtime, and we'll work to make sure that the PPL API innovations are supported as well. But let me talk about how we viewed C++, the challenge here. C++, like most programming languages, was not designed for parallelism. So what's broken about it? Well, first of all, the one that comes to mind right away for people is, well, how do I even express something like a parallel for, or a parallel reduce, or scan operations, these others? So, of course, you introduce algorithms. You do something like that. That's the first thing you think of. The other thing, though, that becomes readily apparent is when you look at STL, it's not thread safe. In fact, its APIs aren't even defined to be thread safe. There are APIs that can't be made thread safe. So the next thing you do is every time you call STL, you just slap a lock around it. Well, that doesn't lead to very scalable programs. So this is an area that I think we understand as an industry we need to make some progress on. So threading building blocks offers some solutions here. You see the same thing with PPL, and we have to go back over the data structures that our languages support and figure out how to make them concurrent. One that's kind of just interesting is if you look at Q, if you want an example of when the API is not thread safe, well, there's no pop if present available in STL. And you can't go check to see if the queue is empty or not and then do a pop unless you put a big old lock around it. You wouldn't be thread safe otherwise using standard STL interfaces. So one of the things you have to consider with making things thread safe and making them highly concurrent is, did you even provide the right interfaces? So one of the interfaces we provide in the queue is pop if present, so that we can make one call in. We don't have to do a lock to prevent somebody else from popping it after we decided that we could do a non-blocking pop. Task scheduler, this will get replaced by and large by the concurrency runtime, but having a task scheduler so that you can just program in terms of task instead of playing around with Windows threads and doing it yourself, very, very important. Synchronization primitives. This is a portability issue. The language, C++, doesn't define synchronization primitives. Those are layered on depending on the system you're on. And having a more portable mechanism is important. In fact, when people say that Java is written for parallelism, they're really referring to the fact that it has a few primitives in it that are just portable across multiple systems. Memory allocation. Having a thread-safe memory allocator that's thread-aware, very important. You can get some people use TVB just for the memory allocator because it'll give a performance boost in a threaded environment because it doesn't reallocate memory to a different thread if it can avoid it. So it keeps sending it back to the same thread that had it before, and that gives some cache improvements. And finally, a couple of utilities. One of my favorite, tick count. The first thing people do when they write a parallel program, it seems, is they want to time it and figure out if it ran faster than the sequential version. Writing a thread-safe thing that's fine-grained gives you fine-grained feedback. A very common question our support team gets is, it didn't run faster, I don't think, and then we look at it and figure out they didn't know how to time it. So we put that utility straight into the threading building blocks. Another thing we found, though, very recently, this will give you some idea of trends. It's very fascinating to watch what customers do with things like this, what our customers are doing. One of the things was they kept asking us for oversubscription. And the reason was they wanted to get some I/O threads that are commonly blocking running concurrently with the task threads, the ones that were doing computation. And so they wanted TVB to lighten up a little bit and allow them to do a little oversubscription so that they were fully utilizing the machine. And we added that this summer, and we're looking at some advances in that. It's a kind of a crude model right now, but we know customers are getting good things out of it. So this ability to selectively oversubscribe the number of threads you have so that you have a few more threads in software than you do in hardware can be important. Another thing is these darn caches in memory. They aren't getting better. You'd like to think you could just write a program and ignore them, but caches have gotten to be more and more important in memory hierarchy, and with future processors moving more and more to NUMA, where memory isn't consistently the same distance from each hardware thread, this gets more important. So there are some concepts in threading building block now to help with affinity, and we're refining those, and we're paying attention to what we can do and more. But one thing we don't want to do is we don't want to ask the programmer to tell us which software thread to lock down on which hardware thread. We have plenty of studies and evidence that says that that doesn't work as well as anyone thinks it would, including me. I'm constantly frustrated by the studies, but when I look at why that doesn't work, it's because occasionally letting a little flexibility in there actually helps things. The problem is you don't want arbitrary migration going on because that gives you bad cache effects. So what we ended up with is a way for the scheduler to keep track of where it had put things before and just kind of hinted it to do that in the future. This is an area where we continue to need to innovate. This is an area of extreme interest for us, is how can we build something that's memory effective with memory without putting the burden on the developer to manage it all. And then finally, a much-loved new feature of the proposed or the draft C++ standard is lambdas, because you get to see all these cool coding examples all week where you used a lambda. Well, when we introduced threading building blocks a couple of years ago, it didn't exist, and you had to write your program like this. You had to take the cool little code that you wanted to run in parallel and go put it in a class function, and I hate teaching it this way. So we love lambdas because lambdas let us write the code this way. And we're looking for what are those subtle extra things that might get added to the language in the future that help express parallelism, because you want a small fragment of code to be able to go in parallel. Now, bringing us back. So we've got Parallel Studio with threading building blocks, OpenMP, going to be on top of concurrency runtime when that's available. I mean, the products will come out hopefully about the same schedule. And the last thing I wanted to mention as far as innovative, forward-looking tooling that we're doing, gave you some overview of some of the problems we're addressing with TVB and how concurrency runtime will help us there. Another area of keen interest for us is data parallelism. And what's interesting about this is we've had this solved before. We had wonderful programming languages like APL, you know, where the notation is the language. And we're looking at this again because data parallelism, you've heard it emphasized a few times even just today, as a key way to get programming. The challenge is that when we write it, it's often obscured by our programming languages. It's easier to write in MATLAB or Excel or in APL or even in Fortran 90 than it is in most of the languages most people use these days. So we've taken a look at, you know, what can we do. There's various levels of data parallelism, and there's a research project at Intel called CT that makes it possible for either CT, the top bar is supposed to say CT can do this automatically. Apparently not, since it's not a product yet, or we can let the user decide which level to work on. So this is a very big area of research at Intel, is what can we do programming language-wise or structure-wise to help with data parallelism, to make that pervasive in the industry as a easy-to-do thing, because that's really a great way to exploit parallelism. So with that, our next topic is going to be, you know, dive down a little bit lower. Now you got, you know, some tools, you're trying to fix C++, trying to do different things, look at the issues at the language level. We can go a little bit lower than that and talk about shared mutable state, and we can either decide to try to make it easier or to try to make it go away. So I think let's let Dave talk about how we can try to make it easy.
Thank you very much. Hi, I'm Dave Detlefs. I'm an architect at for the CLR in Microsoft, and I've been working on transactional memory since I came to Microsoft about 3 years ago. And if you've probably heard little references to transactional memory in previous talks earlier today and earlier in the week. In fact, if you heard Anders in a panel session express a considerable skepticism about it, you realize it's not just a future thing, it's maybe a medium or longer-term future thing, but it's still promising. So what is transactional memory? The basic idea is that you're going to write something like an atomic block, atomic some body, And that body is going to be executed with the A and I properties from the database ACID properties. So this means it's going to be atomic, that is, it's all or nothing. You're not going to have a partial execution that halts in the middle, leaving you with partial side effects and invariants that are violated. It's either going to do nothing or everything. And it's going to be isolated. You can think of it as if it's running as the only thread running in the system, at least if all the other threads are properly synchronizing by also running transactions. As far as the other things, memory transactions are not durable. There's no writing to stable storage on commit. And consistency in the database world has to do with enforcement of user-defined invariants at commit time. That's not a property we deal with here. So Microsoft's DevDiv has had an incubation for 3 years now, trying to implement this. That's been my major project for managed code. I try not to oversell transactional memory. Programming with it feels much like programming with locks, except it's simpler in a couple important ways. There's two questions you have to answer when you're programming with locks that you don't have to deal with when you're programming with transactions. One is the accounting problem. What lock protects what data? You're programming, you realize, ooh, I'm accessing some shared data. I better acquire some lock. What lock is it? Oh, well, if you're a conscientious programmer, you've maybe adopted some comment formalism, and you go and look. But we don't give you much help for that. Nobody else does either. You have to, programmer elbow grease is all that's going to help you there. Problem completely goes away with transactions. The atomic block didn't specify any lock to acquire. It just said, be atomic. It's as if there's conceptually one single implicit global lock. The arguably even more important is, in what order do I acquire locks? Everyone knows that if I don't have a consistent locking order, then I can get deadlock. And in my experience, in large programs, the lock orders can get very complicated. Even if you, as many people do, implement some sort of dynamic checking regime to make sure you acquire locks in the correct order, when you do some maintenance and you mess this up and you get, all right, I've made a mistake, but how do I fix it? Sometimes even that can bend your mind. Again, the problem goes away with transactions. Transactions compose. It's as if the single global lock allowed recursive locking. And I'll illustrate that more in a couple slides. I want to make clear some problems that transactional memory does not solve. First of all, it says nothing about how you introduce parallelism. Things like the task parallel library or the thread building blocks, the parallel for. There's many ways of introducing parallelism. This has to do with once you've introduced parallel activities and they're accessing shared mutable state, this is an easier way to coordinate them and make sure they access them in an appropriate manner. It has nothing about, it does not guarantee that you have correct synchronization. If I had a program that had two threads accessing the same data, one acquiring a lock and one not, that would be a race condition. If I have the same situation, one using a transaction and one not, that's still a race condition, at least in our model. Obviously, it doesn't make your programs correct. That's still up to you. Let's illustrate this composition property. On the right, I have a class account that has an update method that updates the account balance by some delta. Clearly, the plus equals is short for read the balance, add something to it, write it. That is, read and write has to occur atomically. So you'd either use a lock, or in the case of transactions, you'd use an atomic block. Now let's say I have a transfer method that transfers some amount from one account to another. I want that transfer to occur atomically, so I make an atomic block enclosing that operation. Dynamically, the outer transaction has inner transactions in it. What happens? Well, the right thing happens. The outermost transaction boundary determines what is atomic. I'd like you to, that's pretty simple, I hope you would agree. And I'd like you to think for a second of how complicated that would be in the locking world. I'd have to, A, make sure that the account class exported some object to lock to get access to the account, and I'd have to have some total order on all the accounts so I could decide which of the from and to I acquire first, and I have to test and acquire the locks in one order or the other, depending. That gets very complicated, and this is much simpler. Illustrate that in another way. Let's say I had a portfolio abstraction that had several accounts, and I'd like to have one operation that gave me an atomic snapshot of the total balance while still having these transfers. Again, the locking issues, trying to do this in a fine-grained manner with locks are quite difficult, but with transactions, it's just dead simple. So what is the performance proposition of software transactional memory? It's definitely a trade-off. You pay a significant sequential overhead because of the instrumentation of the code you do to do the locking. I'll explain more about that in a minute. But the upside is you get potentially excellent scaling with very little programmer effort. Programmer effort similar to what you would do for doing coarse-grained locking. And there's two reasons for this good scaling. One is, as a mental model of the implementation, you should think of fine-grained reader-writer locking automatically inserted. And in our system, this is at the per-object level. This is the source of the scaling, but it's also the source of the overhead, as you might imagine. The second reason for good scaling is more subtle. The ability to roll back a transaction and possibly re-execute allows you to use optimistic concurrency control. So this basically means if I'm going to read some data, I read some version number associated with it, and then I go through and I get to the end where I want to commit, and I make sure that that version number is still the same. No one came in and modified that data in the meantime. So that transaction, if all the memory accessed by the transaction has that property, then the transaction is consistent and can commit. But the fact that I only read and I didn't write to any shared location really allows for excellent scalability. If I had acquired a reader-writer lock where the reader-writer lock has a write to a shared location within the lock, say to update the number of threads holding the reader lock, even that can kill scalability in a lot of cases. So I'm not going to, here's a performance case. Red-black tree is a balanced binary tree implementing a set abstraction. Each thread does 10 to the 7th random queries on this set for membership. The yellow line is just synchronizing the whole thing with a monitor lock. Obviously, it scales not at all. 8 threads takes 8 times as long as 1 thread. The STM case scales pretty much perfectly. At 1 thread, you pay a significant performance overhead, 3x or so, but at 8 threads, you're winning. So that's the trade-off for the state-of-the-art today. I'm not going to claim that if you did some writing, the curves would look different, not quite as well, but this is a rough flavor of what makes transactions attractive from a performance point of view. And I want to close with, it's not just parallelism that transactions help. You can simplify a lot of other programming issues as well, especially error handling. In our model, if control flow exits an atomic block via an exception, we're going to roll back the partial side effects of the transaction and then propagate the exception. The reason is the other choice would be to commit the transaction with those partial side effects and go on from there. We chose to roll back because we assume that exceptions represent unexpected error conditions, and we think it's better to roll back to a state in which possibly violated invariants are reestablished and continue onwards from there from a semi-known state than it is to try to continue from a completely unknown state. To illustrate that, consider the following. I have 2 abstractions, A and B, that have mutate operations. And I want to make a coordinated update. I want to do A.mutate and B.mutate. In the current world, what do I have to do? I have to do something like, well, I'm going to do try block. I'm going to do A.mutate, record the fact that I completed the A.mutate, and then do the B.mutate. If either of those raises an exception, well, I'll figure out if I've already done the A.mutate, I better do some unmutate operation, and then I can rethrow the exception. If the programmers of A.mutate and B.mutate, they have to have already been careful for this to work at all. They have to test all the conditions that might lead to throwing some exceptions before making any partial side effects. So this depends on them being exception safe in that way. And it has to be possible to write the A.mutate operation or synthesize it from the existing interface. In the transaction world, all of that goes away. You're just going to revert to the initial state as long as A.mutate and B.mutate just have memory side effects, even if you weren't careful, and you don't have to write the unmutate operation. And in a lot of situations, we think this can lead to interesting simplifications of code. So in conclusion, we think transactional memory is a very interesting model. It simplifies parallel programming in a lot of ways and also a lot of error handling code. I want to emphasize that there are many only partially resolved issues that we're not going to be able to discuss here unless you ask me some leading questions. Things like memory models, I/O, that is side effects that we don't know how to roll back, writing to a file in a file system. And there's also significant possible impediments to productizations of this, not least of which is that sequential performance. Maybe that hardware support might help, at least for small to medium transactions. But I still feel hopeful that in the fullness of time, something like this will be able to help you write your programs. All right, thank you.
I want to say a few words about transactional memory as well. One of the things that we've done at Intel is that we actually did put together a software transactional memory compiler, a version of our compiler, and made it available about a year ago. And we've had a lot of feedback on it. I have colleagues at Intel that are anxious to put something in hardware. But we all agree that we don't know what to put in hardware yet. And I'll say a word that actually Sun is putting some stuff in hardware. But let's... I wanted to talk a little bit about what did it take to put it in a compiler. What were some of the hidden things? This looks really attractive, right? You got a little bit of code, you put a lock around it, it can't run in parallel. Voila, you put the word, in our case, TM atomic around it, and magically it runs in parallel. Looks like a nice programming model. There's actually some interesting twists here. It's not quite as simple as you think, but it's pretty close. But how on earth do you get there? Well, requirements-wise, we've got one of the things we've learned working with people when they implement programs is they're not willing to bound how big the transaction can be. And this is the great hardware-software debate with the transactional memory is the hardware guys are all ready to build up little buffers, like 10 long or 20 instructions long, and that can be our transaction. Well, what happens when you have a 20 instruction buffer and you have 21 instructions in your atomic block, or when you nest them endlessly? What we found with programming is for this to be really attractive, it needs to be unbounded. Unfortunately, we haven't come up with an unbounded hardware technique. Well, you might think, well, let's just get that bounded thing in the hardware and then go beyond it. When you go beyond it, do an assist. Well, we've also found out that if you don't have consistent performance, if you fall off a cliff, then you start explaining, well, 20 instruction atomics are really efficient, but 21 instruction long atomics are horrible in performance because you fell off the hardware. That doesn't go over so well. So we've got some real challenges there, and I don't think we have a good solution for that. And the nesting of transactions is extraordinarily important for composability. One other little twist, we need to know when we're in an atomic section, if we call a function, that function needs to be compiled with instrumentation. Now, we actually have a clever technique in the compiler where if you call an uninstrumented function, we'll go into a mode where we act like you had a lock around the atomic. We'll go into an exclusive mode. Well, that doesn't help you with performance, but at least the program still runs. These are extensions we had to add to annotate functions, and you can either annotate them as I'm only going to call it from inside an atomic, or I want the flexibility, or if you don't say anything at all, it'll assume that you're not calling it from inside an atomic. When you say that you want the flexibility, it compiles it with instrumentation and without and selectively calls it. That might give you a hint. We did this in a native compiler for C and C++. This is a little easier in managed code. In managed code, at least you have the opportunity to know whether you're in atomic or not and potentially rejit or recompile your code that you're dealing with on the fly. We can't do that in native code. So this added a little bit of ugliness to the implementation. But we did get it there. We are able to support unbounded transactions. We use a weak atomicity, which is another topic we didn't talk about, which is we only enforce atomics between atomic sections. Things that might need to be synchronized that aren't in atomic sections don't have any defined meaning. And so we've got, we have to support atomics two ways. One is the compiler actually does some stuff, and then we have a runtime library that detects things, that takes care of tracking the memory accesses, doing rollbacks, and so on. Both of them have this concept of being able to go to a single lock mode if bad things happen. In one case, the compiler, if you actually call a function that's not instrumented, it'll go into a single lock mode. But interestingly enough, the library, if you keep aborting an atomic section over and over again and retrying it because something else is interfering with it, after a certain number of retries, the library will say enough is enough, and it'll put a lock around it and make sure that that one finishes. Just an interesting twist under the covers that you have to deal with. So here's a little bit of code that shows, the first function is instrumented, so it can be called. The second function isn't declared anywhere here, so it has to be assumed that it's not instrumented for transaction, and it turns at least that part of the atomic, actually it turns the whole atomic into what's called an irrevocable mode, which means it's no better than having a lock around it, but it still works. Now, a couple of things just to point out that the industry is very interested in this. So Sun Microsystems, and the wonderful graph here is also a red-black numbers, which is often a favorite with STM folks, out of a paper by Sun showing some results in their simulation environment. But they have a processor. It's supposed to come out later this year or early next year called the ROC processor that is going to be the first processor to support hardware TM. And there's a lot of papers. If you're interested in this, it's very interesting to look at their solution to the problem and what they're doing in their processor. We're well aware of this. We're not quite prepared to take the leap. This is a great experiment. I think it'll help all of us understand the problem a little better. There's a lot of projects around with software transactional memory from a lot of places. We've got our C++ compiler available. The favorite in the community among a lot of people is Haskell, and this is Simon Peyton-Jones, who's part of Microsoft's research lab in Cambridge. Works on this extensively, and his site is probably one of the more interesting ones to go to learn more about Haskell. It's a functional language, so it's a rather, you have to bite off the functional and the software transaction at the same time. IBM's got a transactional memory compiler that they just released. There's some work, there's a high-performance group in Europe that's working on extensions for GNU. And if that isn't enough for you, go to the Wikipedia webpage, and they list another dozen or two of them. So anyways, not a very controversial panel so far. You'll have to ask questions to find out where the controversy is. But transactional memory and software transactional memory is certainly very interesting. And if we can do this, it'll give us a low-level underpinning that'll make it easier to build tooling on top, even though I don't think programmers will use it much directly. But we're not ready to deploy this in a big way, and we certainly don't know enough about the usage and so forth to be ready to commit it permanently to hardware. So now with that, that's how we make shared mutable state more easier, but I think the next panelist is going to say just forget shared mutable state. Let's ignore it and let's do something better.
Okay. Thank you, James. I'm Nicholas Gustafsson. I'm an architect on the Parallel Computing Platform team at Microsoft. And indeed, I will suggest that if the problem is shared state, then let's not use shared state. It may not be practical in all circumstances, but it is practical in many. We call this agents as a programming model. It's also called actors, and they're pretty much synonymous. It's all about partitioning state. You have state. State is important. We're not taking a functional programming approach here. We're saying state is there, and mutation of state is a model that has worked for a long time in programming. We just think that we need to reduce the complexity of the state that you're accessing from multiple threads at the same time. Reducing the complexity is important for correctness because you now know what is changing the state at what point. But it's also, partitioning the state is also good from a performance perspective because you actually force yourself to think about what chunks of data you have or what big groups of data you have, which will improve your locality and working. I mean, it'll partition the working sets and therefore have better cache performance also. Another aspect of the agent programming model is message passing between components. So that you have components, these are the agents that have their shared their state that's mutable, but between the components you share nothing. Or rather, you share data only in a safe way, and you do that by passing it as message. And message passing here means that you either copy the data that you need to communicate to another component, or you pass data that's immutable. Immutable data is always safe. Or you have mutable data that you transfer ownership of. And when you're basing your model on data exchange, you don't have to think of synchronization specifically or in separation from data exchange. They become the same thing. So passing messages back and forth between components is how the components synchronize their actions. They're not synchronizing their access to shared state because there is none. Okay, asynchrony here becomes very important. If you're going to wind up with a parallel application, your components need to interact asynchronously with each other. If they're synchronous, then there's no, and each agent, which is an important part of this model, is logically serial internally. You have to have asynchronous message passing or asynchronous interactions in order to actually realize any parallelism. All right. It also frees up some of the interdependence. It's a more loosely coupled model than one where you make a function call or a synchronous interaction of some sort to another component. If the other component takes a long time completing its work, you're now now locked up by that component, so you're more tightly dependent on it that way. This requires a new way, and there's no way of getting out of this. This requires a new way of designing your programs. It's also already supported in existing patterns, not just for these types of agent-based programming models, but for asynchrony in general. We have in .NET the async result and the async programming pattern programming model. We have frameworks like the CCR. If you went to the robotics presentation on Tuesday, I think it was, you saw the CCR, which is a continuation passing style model. We have promises, which is a kind of variant of futures, if you will. It's a little bit richer than futures. We have data flow networks and the good old events. They're all asynchronous programming models, if you will. I think, however, that in order to really break through the productivity issues with the existing patterns and the existing methodologies, and also to enforce some of the rules that we want to enforce for this model, we need some language support. We need formalism around state partitioning so that it's not just up to discipline. Because discipline, when you're up against a hard problem or it just is, you're almost there, but you just have to take a little shortcut somewhere, the whole model breaks apart very quickly. So you have to have something that is enforcing the rules around state partitioning, and that can be the job of a compiler of a language that actually defines some coherent semantics for that. And also the complexity of asynchrony is you can program asynchronous programming models yourself in a framework-based approach, but language here has a great opportunity to make that much more productive. We have actually an incubation project at Microsoft that is doing this. It's called Maestro. It's a special purpose language that is only there to form the outer component layer of your application. And from it, you access any .NET language. And the logic in your C# code or VB.NET code can be completely serial and have no understanding of the fact that it's actually running in a parallel context. The message exchanges and the asynchrony is taken care of in the top level of your architecture by by the Maestro code, which looks a lot like C#, by the way. We call it an orchestration language because when you're, and this is why it's also called Maestro, is because you're orchestrating all these asynchronous interactions in one component and in one body of code. What Maestro does is is exactly what I talked about earlier. It partitions state into domains that are acted upon by agents. This is kind of a little picture of this. We have domains that are really closed-up dwellings, if you will. That's where your state dwells. And your agents are the actors in that. So you can't just reach into a building and start shuffling the furniture in there. You have to have somebody on the inside acting on your behalf, and that's the agent. So domain is just a bag of state, and the agent is your logic acting on it. And it does that by accepting messages from you, little letters in mailboxes that give it instructions. And it's obviously free to send you a letter back saying that, no, I'm not going to do that. That's not a violation of the protocol here. And the letters are schematized. The letters have a definition of what they need to look like and what the values in there must be. And that's sort of like a form that you have to fill in when you make a request. So that's the model in essence. And I'll just leave it there and turn it over to Sean to talk about tools.
Hi, I'm Sean Nordberg. I'm a group program manager at Microsoft. I work in the parallel computing platform team. And you've heard a lot from us this week about parallel computing. What I want to talk to you briefly about today is the notion of tools and what kind of tooling support you will need to achieve parallelism in your applications. And typically what we talk about and what we think about when we're talking about constructing parallel applications is this kind of a schematic around an understanding of tooling. From design through validation, you all know that tools are an incredibly valuable part of how you bring value to your customers and to your end users. And so when we talk about tooling in the design phase, for example, we think about issues of being able to design and design applications where you don't have a parallelism debt to start with. A lot of our code today does have a parallelism debt because we just haven't implemented parallelism yet. In the debugging phase and the optimizing phase, which we showed you tools that we're going to ship in Visual Studio 2010 this week in a session yesterday morning that Daniel Moth presented and in a session on Monday that Hazem Shafi presented, we are tackling questions of programming model and abstraction in the debug experience. And in the optimization experience, we're trying to get to the point where we can really provide a very rich experience around profiling threaded and parallel applications. And then finally, in the validation component is about correctness, really. And even our notions of testing have to begin to change as we think about the massive quantities of data that we'll be able to process with parallel computation. Some of the trends, and these are fairly obvious statements, I'll admit that up front. These are ongoing. These are not new at all. But some of the things that we can think about as they apply to parallelism, it's really about this notion of the complexity that parallelism introduces, and particularly these 3 points. First, if you're going to be programming in these new programming models, things like tasks, which if any of you heard or went to the Daniel Moss session yesterday on, you got a very rich understanding of what the task model is in TPL, or agents, as Nicholas just described to you, then you understand that you don't want to be thinking about threads in your debugging experience. You want to be thinking about tasks or agents. So in a task example, you want to know what tasks do I have running, and in an agent example, you want to think about breakpoints on message send, message receipt, message process, rather than functions and methods. We think that there's going to be a deeper presence of implicit and explicit tooling in just your overall edit, compile, and debug cycle. And what does that mean? That sounds kind of vague. A, and B, some of the skeptics are going to say, well, you're a tools guy. Of course you're going to stand on stage and say something like that. And the notion here is that if you think about the evolution of, say, the IDE from what used to be largely a text editor into a really what is now a full-fledged productivity application, you can think that there's a lot of things going on under the covers implicitly that help you get the features like IntelliSense. And we can assume that we'll see continued work in this way around identifying areas for parallelism in your code automatically for you. That would be a great feature, wouldn't it? And we think that there's work to do in that area as well. So, and then the last one, the role of visualization. For those of you who were here earlier for the presentation from Jerry of Intel, you saw notions of visualization and how they're going to play a really broad part of any of our computing experiences. But specifically around tooling, we believe that visualization is going to be an even more important part of how you understand and interact with the model of your application and the code itself. And we have a couple examples of how we've done that today in the near term. Particularly in Visual Studio 2010, or in the visualization case first, just to continue that thought, we have a multi-stack view in the debugger. And so what this is going to provide is a cactus stack style view of the interaction of your tasks and your threads. And this is a new visualization that we borrowed from other notions of distributed computation and are applying to a parallel debugging scenario. But this is an example of how we think visualization is important going forward. For those of you who saw our profiler work either at our booth in the exhibition hall or at Haslam's session Monday, then you saw that we have these new timeline views that are showing you the thread activity that is underneath your application and the ability to think through execution delay and execution time in a new way that hasn't been available before in Visual Studio. In the notion of programming models, you saw that the debugger, for example, in Visual Studio 2010 will support tasks in the mainline debugging experience. Some things which are a little farther away for us, we wouldn't characterize as near term. There's no notions of shipped vehicles for these or productization even yet. But some things that our team is thinking about in the area of tooling for developers, race detection. This is a very difficult problem, and it's a big impediment to achieving parallelism, speed up in code, and correctness in code. And so what we're doing is working with the Microsoft research team, who has come up with this tool called Racetrack. It's a dynamic analysis tool which detects race conditions in code. A little farther away, even deadlock detection. We've just begun work to think about deadlock detection and how do you detect underlying deadlock conditions in code. And then last, on the test side and on generating test cases and trying to understand particularly deadlocks, races, and live locks, our team internally uses a tool that was talked about yesterday as well at 10:30 called Chess. Chess is a tool that the Microsoft Research Group is also working on, and this is a tool which we use that helps you understand thread interleavings and execution patterns and helps you understand and get to a point of understanding where your deadlocks and races and other things are. We use this tool internally ourselves. I also say that there's a MSD in Magazine article from June of 2008 written by two of the testers on our team that talk about our use of Chess if you're interested in that. And even farther out, let me point the clicker the right way. Even farther out, these are just things that we know, we believe are important overall, and we don't have short-term announcements around these, but things like extending our debugging and profiling workflows to distributed computing scenarios. You can imagine a world where you have parallelism on the client, you have parallelism in a distributed computing scenario, and wouldn't it be great to get a combined view of everything going on under the covers at once? Things around side effects analysis for our parallel for constructs is another area. Like we mentioned, debugging and profiling of message-based application architectures. Actionable performance guidance is an interesting one. In our performance feature for Visual Studio 2010, we're giving you a lot of data. The really hard nut to crack is how do I give you something very, very specific that you can take action on? And we have some thinking around this, although it's quite a ways out. The last thing I'll mention in this area is we talked about at the very beginning, design tools that help you start with no parallelism debt and how to design implicitly parallel applications. And that's the end of my discussion.
Okay. So since this is a panel discussion, we really want to hear from you. You ask questions of the speakers or try to spark some controversy as James instigated. Now, to encourage you to come up to the mic and ask our speakers questions, we have 4 of the concurrency programming with Windows books, which is the #1 selling book at the bookstores downstairs. So for the first 4 people coming up to the mic and ask our panelists questions, each of you will get a book. And of course, we still want you to ask other questions, but we have 4 books to give away. Okay.
We have a winner.
All right, we have the first
All right,
audience asking
great.
questions.
So this is on? Yeah. So my question is, with
Can you please say your name, and also if you have a speaker or topic you want the speakers to address,
Sure.
can you state that
Sure.
also?
My name is Daniel, and my question is for, I'm sorry, I can't remember your name exactly, but it's for the transactional memory implementation. Are you talking about the gentleman in the middle there?
Dave Detlefs.
Dave, thank you. All right. Yeah, so my question is, in that implementation that you have, how does the runtime sort of figure out the difference between doing a single global lock and what you're doing with the atomic blocks that sort of implements a finer grained locking mechanism?
I'm sorry, I meant to imply that the semantics should be as if there were a single global lock, but you should be able to reason about it that way. But on the and the actual implementation, 2 threads executing atomic blocks can be parallel unless they access the same data.
Yeah, okay, so my question was really, I should have made that clearer, but how do you keep track of what data that each atomic block accesses to figure out what level of fine grain versus coarse grain locking that you can implement under the covers there?
In the current implementation, I think this is pretty much the same for all of the implementations, including the Intel one, each read and write is instrumented to be preceded by some sort of fine grain locking primitive. Like, for example, I mentioned this optimistic concurrency control version number based thing. So if I was going to do a read, I would read the version number of the object before reading the field from it and record that version number in a transaction log. At the end, I would validate that transaction log, making sure that none of the things I had read had been modified by some concurrent transaction.
I see. Thank you.
Hence the 3x.
A real quick comment. One of the things that we do very aggressively in our compiler is try to optimize away the instrumentation. So in a logical sense, you instrument every read and write, and then you try like heck to figure out that not all of those were necessary and get rid of them. Otherwise, the performance is absolutely horrible.
Likewise.
Yes, my name is Dave. My question is about writing concurrent or parallel programs in both a shared memory system and a non-shared memory system, and which approach you might want to take to support both. Like, what kind of toolkit would you use with message passing, for example, or are you thinking about maybe bringing in support for like MPI into any languages or into the platform?
Okay. Should I take that perhaps? So MPI is a framework, and there's a .NET version of MPI today. I believe it's open source, but in a solution where we bind language to message passing, we will certainly take care to bring API or MPI into the model so that we can interact with it seamlessly, if you will. There are other message solutions like WCF, for example, that's already used for service-oriented architectures, which have a lot in common with agents, if you will. The assumptions that you can't reach the memory and internal state of the service is exactly the same as not being able to reach the state of a domain. It's just the scale and the constant of the latency, if you will, that's different. And I really think that on your original question, how should you think about the task-based concurrency? I think that was what your question was. The task-based local concurrency versus the non-shared state concurrency. I think they go hand in hand. And where you have data parallel problems, for example, you really don't want to necessarily, at least if the data volume is small and you can solve it on a local node, you really don't want to turn that necessarily into a message passing problem. If it's structured well and you understand the dependencies of data, there's really very little risk in doing a shared state, like a for loop over some matrix or whatever, right? Those types of problems are safe just because of the structure of the data. But if you really want to interleave I/O with concurrency and you want to have, at the large scale of your application, some assurance that you can do things locally and know that you understand the extent of what you're doing and where all the references to data are, you would want to try to look at a more isolated model and understand, what in order to cut down the dependencies of data on each other so that you can actually understand it.
Yeah, if you truly want a program that scales large, you have to go to something that ends up being fairly coarse-grained, and you control the movement of data so that it's not shared to death. So models like, MPI is a framework that sort of forces that, but frameworks like agents, was being talked about earlier, if you can have the discipline to keep your data separate and just pass it, not cheat, you'll get that scaling. We did an experiment with our OpenMP implementation where we have a version of it that automatically transforms the program and uses MPI. And what was interesting is we took the spec OpenMP benchmarks and ran tests with it to see if we ran it on the identical hardware, which was a shared memory machine. If we ran it, though, using the compiled version that forced the segregation of data, the coarseness, and ran it using MPI versus the original version. And what we found is a few of the benchmarks are so fine-grained that it was just terrible. It's just horrible. It didn't work. Most of them ran about the same. 2 of them ran faster when we forced it into MPI, which was kind of amusing to us because what had happened is the compiler actually produced a more disciplined, coarse-grained output that disciplined the movement of data and was more coarse-grained and got better performance than our compiler that most people used. We took those lessons back and thought about them, but that happens with people. Well, it happens with computers too, even when we automated it. If you can have the discipline to to segregate your program correctly, make it a little more coarse-grained, limit how much communication, you'll have a program that has a chance of scaling to thousands of processors and running efficiently on small numbers.
Let me add one short thought more on that. Also, it kind of also depends on what you feel is your performance problem, whether it's latency of a single operation or whether it's throughput. And I think that if the issue is throughput, then will have more luck with a isolated, message passing based model than if it's really latency of some computational algorithm that you need.
My name is Marcellus Buchheit. I wrote my first parallel program in 1993 on Windows NT on a Vice machine, and I showed in a public article that this really brings performance. The bad note, what I see is that in the last 16 years, not much changed. Yeah, we're using multiple mutixes and create thread and all this stuff, and I saw from the first thing it's very difficult. And when I see some 100 million of lines of code or billion of lines of code today, the most developers, they learned a program has exact one begin and exact one end, and independence if it's a real program or a sub-program. And the first challenge will be that I think that developers, they see the challenge, they have to change that thinking and they change their code. Otherwise, we run into parallelist crisis that we have all the hardware available and no one uses it, what we had all the time in our history. I think hardware was always faster than software in solving practical problems. And I remember a little bit of the technology today and what we hear here and also conference. It's like in the 60s when everybody programmed in Fortran and in COBOL, and the 2 usual statements were if and go to. And then in the 70s, Pascal came and C and all the nice programming languages, and everybody learned when you can program something in a block, then do it and forget the go to. Yeah? Don't jump in and don't jump out and use local variables and all this stuff. We have today not a simple method to teach people using parallelism in this manner, and that we need. And the next question is, do we have the tools today? I saw very nice features like Parallel 4 and all this stuff. Is this enough? Is this enough like the the switch statement and the while statement and the for statement and then the go to. Yeah? Is this enough? Can I go to my design team at home and say, okay, our old code, which all this wait for multiple objects and set event and clear event, is this now the right time to reprogram this in a very nice new C++ program with all these statements? And then my developers in 2 years coming, it's not working, it's not safe enough, and now much better technology is available. So do we have to write it again in 2 years? So my question is, on this all two persons, is this the right time to teach people go to parallelism? And are the tools, when are the tools available that you can do that for the next, to create code which have a lifetime of 10, 20 years?
I'll take a shot.
Then we'll tell you why you're wrong.
Sure enough. So I think two answers. One, no, the tools aren't ready yet, in that it's hard. We don't give enough restrictions. You need to be able to, if you really want this to be safe and you want to static checking to say, I didn't have a race condition and this is immutable and thus it's safely accessible by multiple parallel threads. And Nicholas mentioned ownership transfer. All of these things are still moderately researchy ideas. And having said that, I think that the architecture of the programs, the sort of task parallel, fork join parallelism, expose a lot of parallelism, let the system decide how to map it to processors, that will stay. And what you'll get is extra checking to make sure that the things that those parallel tasks you introduce were in fact safe. Where if you go and do it today, you're going to have to do that by programmer discipline. And what will come in over time is backstops to make sure that that programmer discipline was correct.
I was very amused that you mentioned go-tos and block-structured programming, because I talk about that sometimes in my talks about parallelism as an example of how we change. So, in 1968, Dijkstra put his paper out there, go-to statement considered harmful. And it was a few decades of controversy, and now, everybody programs that way. Well, I think a question for us all with parallel programming is how many more of those things are left now that we need to move away from? I think they've all been mentioned this week in the parallel programming classes. The hard part is making those common practices and moving away from them. One that I often think about is we need to avoid, you didn't see a lot of classes on how to use Windows threads to write your parallel program. You heard things about using PPL or TBB or agents or something more abstract. So we know that. But when I get asked the question about are the tools ready, yeah, absolutely they're ready. We got to the moon with assembly language. So either that or they're never ready, right? So we have a long ways to go on tools, but you can write very effective, very compelling parallel programs today with the tools that are out there, and there's a lot of innovation left. I don't know if we'll ever be done, but you have enough tools to go out and at least hurt yourself a little bit.
But I have to answer your question, is it enough? No, absolutely not. It's not even more than a beginning. We need to raise the abstraction level, whether it's through transactional, taking a transactional view of memory, or whether it's constraints on the programming model in some way. Just like, to use the go-to example, a loop is a constrained use of go-to, right? It is a particular pattern, and we need to find those patterns, and we need to establish those, and we need to bind them in some form that lets you use them productively. So are the tools ready? Yes, they're ready. You can do the things, but can you do them productively? That's, I think, the next step. And to allow you to not lose so much productivity in QA, finding the bugs, and making sure that your code is safe. I think that's the next challenge. But the first step is to make it efficient. Creating your own threads is not efficient. Tasks in TPL or PPL or using agents in the agents library that we do in native code, it allows, at least gives you some efficiency. You don't have to spend 3 man years implementing that infrastructure yourself. So it depends a little bit also how urgent you think your problems are.
You mentioned user education, programmer education as well in your question, and that's it's an interesting topic because it's one that comes up a lot in the feature discussions that we have and the design discussions that we have in Redmond around the features that we build, and like what level, it's some form of what level of cognitive load has to go on and for the average developer to really understand what it would take to build a safely parallel program, and then once they've constructed one, how do they verify that that program is going to be correct? How do they understand that they've gotten the speed up that they hope to achieve from it? We're just scratching the surface right now on the opportunities to improve and the tools that we have that help developers understand the parallelism world and to really, quite frankly, to bring it to a much broader audience. And we talk a lot about parallelism for the masses or the democratization of parallelism, and we're just at the beginning of that. There's a lot to be done in the area of education and tools that can help users and developers understand how to construct parallel programs from the get-go. And here's your book.
Yeah, education's a really great point. I get to spend some time with professors, and one of my personal desires is to help see that parallelism gets taught in an undergraduate level to computer science students, and I actually think it's criminal. It's not mentioned in most undergraduate curriculums today. There are a few notable exceptions. Berkeley's being very aggressive about it, but and University of Georgia and Purdue have done some things, but it's a most common suggestion I get back from professors is we've got a full curriculum. We don't know, we can't add a class on parallelism, and that would never be my desire. It's when you teach data structures, when you teach OS algorithms, when you teach basic programming, if you don't mention parallelism at all for 4 years and you send these computer science students out in the world without any knowledge of, no mention of parallelism, I think that's a crime because they're going to live their entire careers out there with it. But a big problem is we aren't sure exactly what to teach. We know a few things to teach, but we don't know everything yet, so people are hesitant about that. And it's a pretty fast learning pace right now, but we are working with a lot of universities, both Intel and Microsoft, to do things to figure out what we can teach at the undergraduate curriculum, and that'll help us as well.
And personally on that, I tend to think that at the beginning of computer science, it was a fairly formal subject. You had disciples of Dijkstra and that sort of thing. And in the past 20 years, there's been people who learned BASIC back in the 70s, and there's been more of the hobbyist and the less academic programmers. I think there may be a switch somewhat back because the skills needed to do parallel programming are more of the formal-like reasoning, and there may be more of a premium on learning the theoretical underpinnings of programming as undergraduates.
Okay, let's go to the next question. And I don't know whether this gentleman is first or that gentleman is first. Okay.
Okay.
All right.
It's a race condition.
Okay. Well,
We'll fix.
thank you very much for giving me the opportunity. First of all, thanks all the panelists and this very, very nice presentations, and the whole PDC is very, very, very useful and informative. Okay, I'm Jim. I'm an engineer. We are doing very heavy-duty engineering analysis. We have using MPI, the public domain library, building some very primitive Planet sort of parallel analysis model. It's running, but it's not very reliable. So my question is very specific. If we use one of those tools, because we hear either tool is handling the managed code or unmanaged code, is there any architecture model or what tools are available to handle both worlds of the code? And what tools or the architecture allow us to build a parallel computation model that take advantage of a cluster of the machine and also the many core locally on a single machine as well?
So you were asking about tools for both clusters
And managed in native.
and managed in native and
then
local.
clusters.
Yes,
Yeah.
yes.
You want to go?
Go ahead. Local tools.
Well, I think your question is about what programming models would you use for managed in native. Is this right?
Yeah.
So we've talked in various sessions about some of the programming models that we have, both on and mostly they're parallels on both managed and native code. We have for task parallelism, and on the managed side we have TPL, which is the task parallel library, which is a lightweight task-based model. We have plink, which is a parallelization of language integrated queries, which is a very productive way of turning something that is already sort of written in LINQ into a parallel query, and it's typically very efficient and safe because most queries are read-only. You read data, you don't write much during your queries. On the native side, we have PPL, which is a task similar to the task parallel library. It has tasks, it has parallel for loops, and so on and so forth. We also have OpenMP. Both Intel and Microsoft are shipping OpenMP implementations. We have TBB, which James talked a little bit about earlier. And we have what we're going to ship in the VS 2010 product. We're going to also ship this thing we call the agents library, which is more of a data flow library for native code. We also have, of course, MPI and MPI.NET that ship with a cluster, the cluster server, HPC product. And so there's a whole bouquet of tools at your disposal.
Does OpenMP working with MPI? If I use both at the same, in the same application,
you can use them together.
Yeah,
we can.
Yeah, if you use MPI on a cluster or MPI.NET, you can use any of the PCP technologies at the node level, and you can also use OpenMP. So you can have an MPI program, and at the node level, have OpenMP code running.
Okay, thanks.
Yeah, it's that hybrid model of doing something different on the node than doing on the cluster. It works. It works just fine. It's often not used, I think, because it means that you have to write your program at two levels. So one of the things that I know the MPI implementations work very hard to do is be efficient at the node level too. So unless you have a real strong reason to decompose your program differently on a node, if the node has multiple cores on it or processors, we see people being very successful just using MPI and not paying attention to whether the core is local or it's somewhere else. And the MPI library hides that and does not send a message. It sends it through shared memory. So you do have that opportunity if you have an 8-core node all hooked together in a cluster of just using MPI and ignoring it. And my experience is that customers generally, programmers generally think they're getting enough performance that way. I very seldom see people jump into the OpenMP mode on the node, even though it's possible and it works just fine.
Okay, can I ask another quick question? Because I asked this for a number of the people at the hall, but I didn't get very good answer. I thought you may give me some information, or some of you here. We noticed that from all this information we collect that if we want to build a cluster, and we have to have all these 64-bit machines, right? Now, what we want to do is, in Office, we still have a lot of 32-bit machines. We want to take advantage of that. So is there a way we can build a parallel computing model that allows us to take advantage of all the 32-bit machines?
Actually, I have a suggestion. We have about 12 minutes left, and I saw that 4 gentlemen have lined up here for further questions. And your question is also related to cluster, and Sharuk here is the architect for the HPC server product. So you can spend some time with him after the panel is over. So I want to go to this gentleman in the red shirt who has been waiting for a long time.
Thank you. My name's Les. My question's about tools. We've heard a lot of sessions about tasks and agents. The one thing I haven't heard, and I'm hoping you can provide a little bit of guidance or some thoughts, is a migration path. If I have an existing native code base that's explicitly threaded, is it a complete rewrite to get to threads and agents, or is
Does
there
it work?
some thoughtful migration path to get there?
Does it work?
Currently,
Yes.
more or less, yes. As
Okay.
hardware moves forward,
Okay.
the threading model is obviously going to be wrong because it's made
does
for
it scale?
a
Does it
specific
scale
number
well?
of threads.
Does it scale well?
With today's hardware, yes.
Okay.
With future
Well,
hardware,
One
Maybe
of the
not.
things is that I suggest is that if you have a threading model that works right now, don't necessarily jump into replacing those threads with tasks or agents or things like that, but look for the new areas for parallelization and use tasks there. And then eventually, if you do want to go into using our technologies, and this is specifically on the native side, the agent library does sort of map pretty nicely an old style thread to an agent. You'll have to rethink if the biggest obstacle in migration is going to be if you're relying on thread local storage. That's also always the got you, where you want to replace the thread local storage with agent local storage. But that's the path that I would suggest is migrating. There's no performance benefit in moving to agents. It's a robustness and correctness. And so if it's already working, you already figured out all the dependencies, you're not going to derive any immediate benefit from that.
okay.
But look for the new opportunities for parallelism instead.
Thank you.
So one other thing you could, that if you did decide you wish to migrate, one question to ask is your use of threads task-like or agent-like? If you're spawning threads and they're sitting around waiting for conditions to be true in a loop, that's obviously agent-like, that kind of waiting for messages. If you spawned a thread to do, if you could have made that thread in its entirety into a task that finishes something and completes, then that's another clear migration path.
A thought on Nicholas's comment about how to identify new areas for parallelism in your current app. If you went to Hazem's talk on Monday, he walked through the new profiler feature that we're doing and did a literal step-by-step demo around here's an application that was single-threaded, and now we're going to add some threads, and we're going to slowly over time build out how much parallelism this application takes advantage of. And you can play with these bits in the CTP. There's a walkthrough around these. And once Visual Studio 2010 ships, then by all means go in and point your own app at the profiler, and you can see literally how many cores over time out of a trace your application is consuming, and then you can go in and look very carefully around the threading and the delay time for your application. So, but definitely take a peek at the video of Hazem's session if you didn't happen to be there.
Okay, thank you.
For what we're trying to do is we're trying to make programming of threading and so forth easier, right? And a lot of what easier,
Yeah.
yes,
Programming is not easy.
and a lot of what is necessary to kind of reason about that is additional kind of metadata. Things as far as knowing what's immutable, what's safe, and so forth like that. And that's a tough problem because when you're reliant upon that, because it's metadata, it has to flow even once the system exists for expressing that. It kind of has to flow through all of the pre-existing libraries before it really starts to become useful. But there doesn't seem to be an urgency towards that direction. I mean, you're talking about making things more efficient right now, whereas this seems to be something that really needs to be higher on the priority list because it's got that kind of delay of going through the whole ecosystem of it won't exist until everybody has kind of adopted this, and then you can start to reason this way.
Anders yesterday in the panel session on the future of programming languages made a comment about how people are often frustrated by the slow pace of evolution in programming languages, and this is yet another example of that. We can't arbitrarily break the people who aren't on the fast path. And yeah, you raise a tough question. But we are thinking hard about these issues, believe us.
It goes to the even deeper than just language. It's really about the type system, and to be truly, safe there, it will affect everything, or at least on the manner side, right? And so it's the type of change that you want to make, knowing for sure that you're making the right changes, because you're going to break, like David was saying, you're going to break a lot of code when you do that. And so you need to know that it's worth it and that you did it right on the first try. So there's a lot of thought going on around this at Microsoft. We didn't cover that in this session, but we're thinking very hard about this exact problem. And you're absolutely right on there. But it's one where we need to be careful about breaking existing code, and therefore we need to be very careful about how we do it. But you're absolutely right.
But when you say we've already answered that first question, that it's worth it, how that you do it right, that's definitely.
I'm sorry? That when we've answered the first question?
Well, that it is worth it
Yes.
to do this.
Yes.
That, I mean, if we're still asking that question, that we're behind.
No, it's given a particular solution to the problem. Is that solution and the pain that it will inflict worth the value that we derive from it? And that you can't really answer that without, well, you really want to try to minimize that over a suite of possible solutions, of course.
Okay, we have 4 minutes left, and I want to answer both of these gentlemen's questions. Okay.
I'll try to be brief. My name's Jim. The question I have is for Nicholas.
Okay.
In my day job, I write algorithmic trading systems. It's very latency sensitive, concurrency, and I've been doing this for about 10 years. So over this time, I've developed a set of tools and kind of design practices that I use. And a lot of them do depend on share state and lockless type algorithms and long-lived threads. And as I've been attending the sessions and as you've been presenting your approach, I've been having difficulty internalizing, at least intuitively, the wisdom of why and where that is a better technique. And what my mind keeps getting hung up on is the notion that by messaging, it feels to me like you're doing a lot of allocation. And I guess I've learned, over, at least in the way that I've been approaching the problem, that allocation is bad. And is there a way that you can explain your approach to somebody like me with my background so that I could understand that that's not a problem, and how you're addressing that issue and maybe understand better the wisdom of your approach?
So first of all, it is an issue, and that's why when we talked about the various forms of making exchanges, there's copying. That's where allocation comes in. You have to allocate memory to have a new place to store the data. You can pass immutable data, and that doesn't seem to be applicable to your scenario. Or you can transfer ownership. And ownership transfer is kind of the discipline that you're implementing when you are doing a pipeline architecture, for example. You have a stage, it gets the data, it does its thing with that data, and it passes it off to the next stage and doesn't look at that data anymore. It really transfers ownership. It does it through discipline, not through formalism, if you will. There's no runtime assurance that you actually don't have access to it anymore. But there are efficient ways of doing message passing under certain circumstances. I tried to not make the claim that this was a panacea or something that would solve all problems, but it is a way of structuring your applications so that you can avoid trouble. Now, that still doesn't mean that it will solve all problems or that there aren't problems where efficiency really centers around doing things on local shared state. So the model is not about eliminating the access to shared states. It's about cutting down the regions of shared state to smaller and smaller pieces so these unknown dependencies between components become more known. That said, it sounds like in your particular case, you spent a lot of time devising really, really sophisticated, I mean, just the fact that you're using lock-free algorithms tells me that you spent a lot of time on that code.
That you're either a genius or a fool.
Probably a mixture of both.
And so there are situations where it's absolutely just that type of rocket science that needs to be applied to address that particular problem. But if we're talking about taking it to the mainstream, not every programmer is going to be able to do what you have done. And that's kind of the core argument behind having this type of model.
That's kind of, I guess, what I'm wondering. Am I solving a problem with a sledgehammer that could be solved simpler, and trying to internalize, because doing all this lockless is not cheap or easy. So
yeah, I would love to go through this after the session with you and just talk about it, pick your brain on it.
And the hope of transactional memory is to automate and make much simpler for similar performance characteristics the sort of programming you're talking about. So especially if you had hardware support for the small transactions.
Okay.
Well, I'm not a rocket scientist, and I actually, it's funny that you mentioned the go-to is considered harmful, because I went to a session on F# in Boston, and the guy who was talking about it said that where we've evolved to from a programming standpoint is from some people's minds broken, and we can't, assuming many core, where we're dealing with thousands of cores in the future. Locking is problematic, and that's why he was saying F# could be the answer. And you were mentioning yesterday that agent programming, based programming, could be the future. So my question is, is locking considered harmful in a many-core?
I made the mistake of writing an article and suggesting that one of the ways to get better parallel programming was to avoid locking. And Herb Sutter called me up right away and said, "Is that really what you meant to say?" And I said, "Why do you ask?" And he says, "What happens in your experience when you convince programmers that locks are a bad idea and that they should use less of them?" And I thought, yeah, I laugh like that too. I said, "Oh shoot, I won't ever say that again, Herb." They may be harmful, but the worst thing you can do with locks is have too few of them. Of course, when you have too many of them, you don't get scalability. So, I think anyone that's a big fan of software transactional memory would tell you locks are very evil. They definitely cause a lot of problems, debugging, scaling, all sorts of things. And if we knew how to get rid of them, we would. I actually don't think they'll ever go away, personally, even if we get transactional memory. But is that controversial enough to get someone to argue with me?
No, I think they're very harmful. But Professor Ed Lee at Berkeley has written a lot of papers on he wrote one paper about the problem with threads. But his point is that what threads and locks really does is it says, here's an incredibly, particularly when you throw in preemption here and multi-core, you have a completely non-deterministic model, which is execution of instructions in a preemptive and multi-core world, accessing shared state, and you're asked to rein that total anarchy in with locks. What we need to do is we need to start with, so we start with a non-deterministic model, and we try to add determinism where we think it's necessary. What we ought to do instead is start with a deterministic model, such as process networks or something like that, and add non-determinism when we need it. It's not that we can have necessarily a completely deterministic model, but let's start with one, and let's add, like this gentleman's problem perhaps, let's add non-determinism where we absolutely need it, because otherwise we're not having a practical solution to our problem. So I think locks are part of the problem, not part of the solution. But I don't see that we don't have anything better today, and therefore, please continue using them.
I see that the door staff have opened the door and they're about to throw us out. So I want to thank everyone for your attention, and I want to thank the panels for such an interesting talk. Let's give everyone a hand.
Thank you.